Welcome all. In this lecture, we'll discuss the synthesis of driving point network functions. We can use two forms for the synthesis. The one is called the Foster form and the other one is called the Carr form. Further, the Foster form is of two types: Foster 1 form Foster 2 form. Similarly, Carr forms are of two types: Carr 1 form and Carr 2 form. If we realize the network function using Foster 1 form, we get a series network. Similarly, if we realize the network function using Foster 2 form, we get a parallel network. Whereas if we realize the function using Carr 1 and Carr 2 form, we get a ladder network. That is, the shape of the function will depend upon the type or the form we are using for the synthesis. If we are using Foster 1 form, we'll get a series network. If we are using Foster 2 form, we'll get a parallel network, and if we are using Carr 1 and Carr 2 form, we'll get a ladder network. In this, we'll be using only the impedance function. That is, the realization of the network is possible only if the network function is given in the impedance form. If it is given in the admittance form, we will take the inverse of it to convert it into impedance form. Similarly, in the Foster 2 form, we will use the admittance form of the network function. We will discuss more about the Carr form in the later lectures. Till then, we will concentrate only on the Foster 1 and Foster 2 forms of synthesis. In the Foster form of realization, we use partial fraction methods. Partial fraction method to decompose the given network function. Whereas in Carr form, we use continued fraction expansion. Let us discuss about the Foster form. We will first discuss about the Foster 1 form. In this, network function is decomposed into many smaller order network functions, say Z1s, Z2s, Z3s, and so on. Here, the degree of Z1, Z2 and Z3 must not exceed by 2. Also, these Z's can be a R component, L component, or C component, or parallel combination of RL, RC, or LC. So the realized circuit would look something like this. We will have a impedance Z1 which will be connected in series with the impedance Z2, and it will be further connected in series with Z3 and so on to complete up the network. Say the last impedance is Zn. So the given network would look something like this. Let us see how this circuit will look for the possible combination of RL. As I already told you that Z1, Z2, Z3 will be either a R, L, C, or the parallel combination of RL, RC and LC. In case of RL, Z1 could be either R or a L or the parallel combination of R and L. So these Z1, Z2 could have the values R, Ls, or the parallel combination of R and Ls will give R into Ls divided by R plus Ls. So this network would something look like this, that it will have a resistance R connected in series with the resistance with the inductor L, and connected further in combination with a parallel combination of R and L, and this will continue like this. So the Foster one form realization for an RL circuit will look something like this. Now to decompose the given network function into smaller order network functions, we will require a decomposition method, and in Foster one form we use partial fraction methods. We'll discuss about partial fraction methods at a later in this lecture. Let us discuss about the Foster 2 realization. This form is also called the admittance form because the network function used should be or must be a impedance function. So let us say we have this ys, and this ys will be decomposed into y1 of s plus y2 of s plus y3 of s plus and so on up to yn of s. All these y1, y2, y3 and yn are the smaller order admittance functions. So here these y1, y2, y3 would be the either R, L, C, or the series combination of RL, RC or LC. The network realized using Foster 2 form will look something like this, that it will have admittance y1 connected in parallel to another admittance y2, further connected with another element in parallel y3, and this connection will continue up till yn. As we can see, all the elements are connected in parallel, so why this is also called the parallel network realization. Before proceeding further, we must discuss the partial fraction expansion methods. The first thing to be noted about partial fraction method, that it can only be possible if the degree of numerator is less than the degree of denominator. That is, to apply partial fraction decomposition method, we must have the degree of numerator to be less than the degree of denominator. If the degree of numerator is greater than the degree of denominator, we will first proceed with the division method. That is, we will write the given expression in the form quotient plus remainder divided by divisor, where the remainder must be of lower degree than that of divisor. The second rule of partial fraction expansion is, say if we have a network function in the form ns divided by s plus a into s plus b in this form, and we are required to obtain the partial fractions of this. So we can write this as a divided by s plus a plus b divided by s plus b, where a and b are called the residues of the pole s plus a and s plus b. Here the residue can be calculated, a can be calculated by ns divided by s plus a into s plus b, that is by multiplying the given network function with the pole and substituting s equal to minus a. This will be a. Similarly, we can calculate b, and this b will be ns divided by s plus a into s plus b and this will be multiplied with s plus b, and substituting the values s equal to minus b. Similarly, say if we are given ns to be equal to s plus a into s square plus b, that is, in the denominator we have a quadratic term, then the partial fraction can be written as a divided by s plus a plus b divided by s plus root bj plus b conjugate divided by s minus root bj, where this a, b and b conjugate are the residues of these poles, and they are calculated in the same fashion as calculated above. That is, here a will be equal to ns into s plus a into s square plus b multiplied with s plus a, and we will substitute s equal to minus a. For the calculation of b, I will multiply ns divided by s plus a into s square plus b with s plus root bj, and I will substitute s equal to minus root bj. Similarly, b conjugate can be calculated as ns divided by s plus a into s square plus b, multiplying this with s minus root bj, and substituting the value s equal to plus root bj. Well, we do not need to calculate b star because it will be the conjugate of b. If it is say plus 2, then this will be. Let us perform some numericals. Here we are given Zs equal to s into s square plus 4 divided by s square plus 1 into s square plus 9, and we are required to synthesize it using Foster 1 and Foster 2 form. We will start with identifying whether the given impedance function is a LC impedance function, RL impedance function, or RC impedance function. We will check it by using the properties of LC, RL and RC impedance function. The physical observation or the visual observation shows that in numerator we have an odd polynomial, and in denominator we will be having a even polynomial. That is, it is the ratio of odd to even polynomial, and the ratio of odd to even polynomial is only possible with LC emittance function. That means this ZS can be realized using L and C. So it will be LC impedance function. After this, we will apply the partial fraction expansion. After knowing that this is a LC impedance function, I can write s into s square plus 4 divided by s square plus 1 into s square plus 9. This will be equal to a divided by s plus j plus a conjugate divided by s minus j plus b divided by s plus 3j plus b conjugate divided by s minus 3j. Let us calculate a using the residues. A will be equal to multiplying this factor with this s into s square plus 4 whole divided by s square plus 1 into s square plus 9 into s plus j, and substituting s equal to minus j, I will get s into s square plus 4 whole divided by s minus j into s square plus 9, because I can write this s square plus 1 as s plus j and into s minus j, and s plus j will cancel out with this. I will be left with s minus j only, and I will substitute s equal to minus j. On solving and substituting s equal to minus j, I will get j into minus 1 plus 4 divided by minus 2j into minus 1 plus 9. I'll get minus j here, and this will be equal to minus j will cancel out with this minus j, and in the numerator I will get 3 and in denominator I will get 8, so I will get 3 by 8. So the residue for this factor is 3 by 8, and this will be, and the conjugate of this will be equal to a star, so I can write that a and a star will be equal to 3 by 8. Similarly, b will be equal to, I will multiply the given factor with s plus 3j, s square plus 4 divided by s square plus 1 into, I am writing s square plus 9 to be equal to s plus 3j times s minus 3j, and multiplying the whole factor with s plus 3j and substituting s equal to minus 3j. S plus 3j will cancel out this factor, and I will be left with s into s square plus 4 divided by s square plus 1 into s minus 3j. I will substitute s equal to minus 3j in this, and I will get minus 3j into minus 9 plus 4 whole divided by minus 9 plus 1 into minus 3j minus 3j, and on solving I will get 5 by 16. As it does not have any imaginary term, so it will be equal to its b conjugate. So now we have calculated the values of a, b, a conjugate and b conjugate. We can substitute them here, and I will get s into s square plus 4 whole divided by s square plus 1 into s square plus 9 can be written as 3 by 8 divided by s plus j plus 3 by 8 divided by s minus j plus 5 by 16 divided by s plus 3j plus 5 by 16 divided by s minus 3j. And on solving I will get 3 by 4. Further solving, the LCM of these two will be s square plus 1, and over here I can write 3 by 8 s minus 3 by 8 j plus 3 by 8 s plus 3 by 8 j. Similarly, taking the LCM of these two, I will get s square plus 9. In the numerator I will get 15 by 5 by 16 s minus 15 by 16 j plus 5 by 16 s plus 15 by 16 j. Solving, these two will cancel out. Similarly, these two will cancel out. I will get 3 by 4 s whole divided by s square plus 1 plus 5 by 8 s whole divided by s square plus 1. Now we already know that the given network function is a LC emittance function or impedance function. That means this must be the network function of parallel combination of L and C, L and C. Similarly, this should be the parallel combination of L and C. Now their general network function will be Ls into 1 by Cs whole divided by Ls plus 1 by Cs, that is the parallel combination of Ls and Cs, and solving I will get Ls divided by LCS square plus 1. Now comparing this network function with this, I will get LC equal to 1 and L equal to 3 by 4. Let me number them L1, C1, L1. So I have L1 to be equal to 3 by 4 Henry, and substituting the value of L1, I can calculate the value of C1 here. So C1 will be 1 by L1, which will be 4 by 3 farad. Similarly, comparing this with this, I will get L2 C2 to be equal to 1 and L2 to be equal to 5 by 8 Henry. Well, oh, there is some mistake. This should be S square plus 9. So recomparing it, I need to make this 9 to be equal to 1. Let me rewrite it. I will get 5 by 81s over 1 by 9s square plus 1. Now comparing this with this will give L2 C2 to be equal to 1 by 9 and L2 to be equal to 5 by 81 Henry. Substituting the value of L2 in this expression, I'll get the value of C2. C2 will be equal to 1 by 9 L2, and this will be equal to 81 divided by 9 into 5. This is 9 by 5 farad. So after decomposition, I have all the values of L and C. I can draw the circuit, and the circuit will be a parallel combination of L and C, L and C, where L1 will be equal to 3 by 4 Henry and C will be equal to 4 by 3 Henry, connected in series with the another parallel combination of L and C, where this L will be equal to 5 by 81 Henry, and this C will be 9 by 5 farad. And completing this circuit, the circuit will look something like this. So this is the Foster one form realization of the given network function. This is Foster one form realization.